So, basically we are still talking about decision in the presence of uncertainty, and so far I have explained to you how to evaluate through the sensitivity analysis the impact of uncertainty on our decisions. And again, sensitivity theory, sensitivity analysis, is a very useful tool, as I said, to clarify what is the effect of the presence of uncertainty on our decision, and especially what are the consequences of a wrong decision, because there is uncertainty in the data. But still, sensitivity analysis doesn't tell us what is the most appropriate decision to take in the presence of uncertainty. It just helps us to understand what is the most appropriate decision, but it doesn't tell us, the sensitivity analysis, what is the best decision that you should take. To solve this problem, there are other methods that typically don't evaluate what is the impact of uncertainty, what is the consequence of a wrong decision. They just serve to the purpose of helping you, to assist you in taking the most appropriate decision in the presence of uncertainty. So they are complementary. They are not basically two competing alternatives. Sensitivity analysis is one thing, and the other methods, among which there is utility theory again, are another thing. And in order to understand, to select the best decision in the presence of uncertainty, again, utility theory, formulated in a different way with respect to what I anticipated to you before, is, again, utility theory is a useful tool. And you already know the basic of utility theory. We basically consider the utility theory in order to determine the weights of different objectives, different targets, and also we said that it's possible to use utility theory to rescale different objective functions. And we already said that utility varies from a minimum, which is 0, to a maximum, which is 1. And we said that when we associate the utility to an objective function, the utility should be a not decreasing function, not decreasing relationship of the objective function. This is what we said. So basically we said if I have an economical benefit, which is probably the most clear example, I can associate the utility to my economical benefit, and the utility function should be a non-decreasing function of the benefit. And it should vary between 0 and 1. This is what we said. Now, utility can be defined in many different ways. I already anticipated to you that once that we satisfy these axioms, non-decreasing, 0, 1, once that these conditions are satisfied, I said I am free of deciding the shape of the utility function, the shape of the relationship that relates utility with the objective function. And therefore, of course, we didn't say how to define this shape. I just said you may take interviews, you may collect opinions, and then this is a way of defining the utility function. Now, the utility function can also be defined in order to solve the problem of taking the most appropriate decision in the presence of uncertainty. Let's see how it can be used to this purpose. So first of all, here there are again the axioms, the conditions to which the utility should satisfy. And let's refer now to a classical problem where our decision is to be taken with respect to one target only, which is the net benefit. So let's refer to this case, just to give you an example. Indeed, I'm providing a theoretical explanation now, which is not binded to the given example. But in any case, of course, using an example helps me to illustrate the method. So let me refer, just for the purpose of illustrating the method, to the case in which you have to take a decision to maximize the net benefit. And your problem is not to maximize the net benefit. Your problem is that you have uncertainty in the definition of the benefit function. And therefore one wonders whether it's what is the most appropriate solution, decision then. Okay, so we are referring to this problem, and therefore we have to associate a utility function to a given benefit. So this is our practical problem, and we have to take uncertainty into account. Okay, these are the conditions to which the utility function should satisfy. Now, I need a definition now. So how to define this utility function, which can be written like U depending on net benefit, which depends on X. So, how to define it? Let me provide a definition, which is characterized by the presence of uncertainty. And therefore, let me refer to two different alternatives. So let's suppose that you go to your stakeholder and you ask him the following questions. Look, what is your preference? Given that you can obtain a net benefit from water allocation, which is varying from a minimum and a maximum. So you have this MV min and NB max. So depending on what decision I take, you get a benefit which is included between these two extremes. And you ask him, what is your preference? If, let's refer to a net benefit MB star, a given benefit. What is your preference? I may give you this outcome for sure. So the first option corresponds to certainty. You tell him, look, you have to tell me what is your preference. I may give you this outcome for sure. Of course, MB star is comprised between min and max. It can be also min and max. But let's make reference to a generic benefit. Or the alternative to giving the net benefit NB star for sure is I may offer you a situation in which you can get the maximum benefit with probability P or the minimum benefit with probability 1 minus P. So let me clarify these two options. One option is for sure you get NB star, which is between min and max. The second option is there is uncertainty, so I may give you the maximum benefit with probability P, or if I'm not successful in giving this, we jump to the minimum benefit with the probability 1 minus P. So, in the second option, according to the second option, you have two sub-options. So what would be the reply of your user? The reply, of course, depends on the P value. If you tell him that P is equal to 1, he, of course, would select the second option. He would say, yes, of course, I take the second because I get the maximum. If you tell him that P is equal to 0, he, of course, would prefer to get, for sure, the net benefit NB star, which is, in general, greater than the minimum. And if you say the probability P is 50%, 0.5, then he starts thinking it. And if he's a person that doesn't like the risk, he would continue to select this. Or he would like to get a very high value of P in order to prefer the second option. If instead he's a person that likes the risk, like a gambler, then he would select the second, even if P is very small. So do you understand this situation? Of course, this is a subjective decision, as I said. Some persons don't like the risk, and they prefer to get the money for sure. Other persons like the risk, and they prefer to run the risk if it gives the possibility to get more money. It's like investing money. Some people prefer the, I don't know how to say in English, the state, I think bonds is the bonds issued by the state. Okay, let's forget about the crisis and the other consideration that one may take. But basically, some people prefer to take to invest the money in governmental bonds, even if they don't take much money, instead of running the risk to get some other bonds which can give more money but are risky. Okay, so there exists, of course, a p-value which makes the user indifferent. I'm not sure this is an English word, like to say, to give equal preference to the two main alternatives. So there must exist a p-value which makes the user assigning no difference between the two options. As I said, this p-value is very high if he's prudent, is low if he likes the risk. So this p-value is defined as the utility of MB star. So utility of MB star equal P, where again P corresponds to the value of the above probability, which makes the user not concerning at all about one alternative or the other. So you see that you can make the same reasoning for any value of the benefit, and therefore you can construct a graph which is your utility function. And of course, this graph starts from MB min and ends at MB max. And on the ordinates, it goes from 0 to 1. So we have 2 points which are sure, which are 0 for the minimum and 1 for the maximum. And then, if you get a MB star, here in between, we already said that the very prudent user would like to assign it a very high p-value and therefore a very high value of utility, while the user that likes the risk will assign a very low utility to this MB star, which means that if you draw in the graph for your reference the straight line between 0 and 1, you can get two curves, one like this and the other one like this. This is prudent, and this is risky. Therefore, the utility theory, it's a mean to quantify your propension or aversion to risk. Of course, this depends on a given stakeholder. The propensity to risk is an individual behavior, and therefore you may need to, if you want to take an informed decision, you may need to mediate to reach a compromise between different utility functions, and this is something that you need. It's an issue of social sciences. I'm not giving more details on this. Perfect. Okay, now that I have clarified how the utility theory can help you to assess the propensity or aversion to risk, let's see how the utility theory then is used to identify the best decision. Now we have to simplify our problem in order to make it suitable for giving to you an example to be developed here. And therefore, let's suppose that we have our usual meaning that we already used it before, benefit function, which includes the cost term. And let's suppose that we have the parameters of the utility function are 4, as you may remember, A, B, C, and D. And let's suppose that uncertainty is given by the fact that only 3 possible vectors for parameters are possible. In general, uncertainty means that any possible vector of parameters is possible accordingly to a probability distribution. But in this case, to make it simpler, let's suppose that this is a discrete case in which we have only 3 solutions. And let's suppose that these 3 possible parameter vectors are equally likely, so they can occur with a probability of 1/3 each. This is a simplified way for representing uncertainty by just limiting the range of possible cases to 3 possible outcomes. And therefore the decision is, okay, so what is the decision, the best X value, given that we have uncertainty here. So we cannot solve this problem as we solved it before, because we solved it before by just identifying the maximum, namely identifying the X value which gives to you the maximum benefit. Now you can't do that anymore. We need to identify what is the best decision by taking into account that the parameters may assume 3 different values with equal probability. Good. So, how can we move forward? First of all, we have to define a utility function. We have to see, these are the three benefit function corresponding to the 3 different parameter values. And you see that the optimal allocation is not unique, of course, it changes. So if you get the first one, you get a value of X, an optimal value of X, and then you have some variability. This is material, something that you have already seen before. And therefore you can identify here a minimum and maximum benefit. You see that the maximum benefit is about 80, and the minimum is close to 0. It will be probably 5. So by analyzing this, again, these 3 functions, you can identify the maximum and the minimum. And we already know something about this case study. We already know that depending on the parameter vector, we have the following situation. I just remind you. So, if the parameter vector by chance is W1, then the optimal decision, we already determined it before, by maximizing the related objective function, is 28, and we get a benefit of 79.22. Good. Now, the optimal decisions for the other 2 parameter vectors are 38 and 42. And then I listed here another possible decision. I picked it up just by chance, 30. So again, the first 3 decisions, 28, 38, 42, are the optimal decision for the parameter vectors W1, W2, and W3. The 4th case, which corresponds to an allocation of 30, I just picked up it by chance. And of course, the table should be longer. I should include any other possible decision if I want to make a comprehensive analysis. But in order to make it simpler, I limit my list of possible decisions to these 3, 4 decisions. And look, if you refer to the case in which your outcome for the parameter vector is W1, then you get 79.22 accordingly to W1. If you change and you compute the benefit for the allocation of 28 with the other two parameter vector, you get different values. Not necessarily these different values are lower. In this case, they are lower, but they could be higher, because I remember to you that if you take the optimal decision for W1 and you change the vectors of parameters to W2 and W3, you could get an increase of the benefit. Okay, good. Now, let's look at the second decision. Second decision, which is optimal for W2. And these are the values of the benefit for the three parameter vectors: 76.26, 76.85, and 63.41. Okay, good. Third decision, optimal for W3. And you see that the benefit with the other two parameter vectors is indeed higher, just because of what I just told you. Now, look. I look at this table by going by rows. If I go by column, now I have in the first column the benefit that I can take accordingly to W1 for the different decisions. And in this case, what I should find is that the optimal decision should have the highest benefit. And indeed, this is verified here, because the optimal decision for W1 is 28, and it's the greater one. Let's look at the second column, and you see that the optimal decision is the second row, and indeed this is the highest benefit, so this is fine. If I look to W3, the optimal decision corresponds to is 42, and again, this is the highest benefit in this column, so everything is fine. And then you can compute here the average benefit and the minimum benefit. Why I included these two columns? Just because sometimes people like to take the decision that maximizes the average benefit or the minimum benefit. I already mentioned to you this possibility. And if you decided to take this way, then your optimal decision would be the last one, 30, accordingly to the criteria of maximizing the average benefit. Instead, if you look at the criteria of maximizing the minimum benefit, then you would go to 42 as better allocation. So if you change the criteria, you take two different decisions. This one maximizes, again, the average. This one, 42, maximizes the minimum. But we already said that these criteria have some weaknesses. We said that if I try to maximize the average, do you remember the gambler's paradox? In that case, these two criteria wouldn't be appropriate, because in one case it would be too risky, in the other case it would be too prudent. So now let's get utility into play. And what is useful, this table is useful because it allows you to identify also the minimum benefit and the maximum benefit. Look, if we refer to this, let's say, discrete case in which we have only 3 parameter vectors that are possible and only 4 possible decisions, then we get a pool of 12 possible outcomes, and only 10. So you can see that the minimum is, I think, 61.18, and the maximum is 79.22. Okay, good. So here, okay, let me anticipate one thing, which is, this is a useful definition, which is the definition of dominated decision plan. In this case, we are dealing with different decisions, and I identified 4 possible decisions, okay? And therefore my decision plan P is just corresponding to X according to the previous case, because you remember that the decision plan is the vector of the decision variables. In this case, the decision variable is just 1, so the decision plan is the same, is coincident with the decision variable. So I could have put big X there, capital X there, instead of capital P. But this is more general. So let me define this decision which is dominated. And it is useful to identify dominated decisions, because you can just discard them. So what is the definition of a dominated decision? Okay, it's very simple. It's very simple, but when I ask this question to students, and then when I ask students this question, it's difficult to get the correct reply, because I think it's a nasty definition. This is the reason why students don't like it, but it's very simple. So let's refer to our given decision plan, which we want to prove to be dominated, and let's refer to any other, to another decision plan P. Okay, so, and this P is general. You can take any other. This definition says that the decision plan P prime is dominated by a decision plan P, sorry. No, it's not general, it's a specific one, sorry. I made a bit of confusion. So we have a decision plan P prime, which we want to prove to be dominated by another one, not by all the other ones. And therefore, basically, if you can prove that the net benefit associated to the decision plan P for varying W is always greater or equal than the benefit that you can obtain with decision plan P prime, what does it mean this? It means that P prime is irrelevant with respect to P. So if the net benefit that you take with P for any of the possible values of W is always greater, then you discard P prime. Greater or equal, you discard P prime. So this is the moral of the story. You compare 2 decision plans, and you look at the benefit that you take with one and with another for any possible value of the parameters. And if you see that the benefit that you can obtain with P is always, for any possible value of the parameters, greater or equal than what you get with P prime, you discard P prime. And this was not the case of the previous table. Sorry. If you get back here, you can't reject any decision. Okay. There is one more condition that I would like to make sure it is satisfied, because here, be careful, I want to exclude the case in which they are equivalent. Here, be careful, I want to exclude the case in which they are equivalent, because according to this definition, they could be equivalent. Therefore, let me include another condition. And the second condition is that it exists at least one parameter vector W prime that makes P prime greater, strictly greater than, P strictly greater than P prime. Benefit associated with P strictly greater than the benefit associated to P prime. If these 2 conditions are satisfied, you can reject P prime. Why should you stick on P prime anymore if it doesn't give to you any greater benefit, and in some cases leads to lower benefits. This is important because you know, you can reduce the range of the decisions to analyze. Be careful, this is a kind of question that you already understood that I can ask it at the exam. And as I said, it's very easy. If you think to it, it's very easy, but it's probably difficult to remember, it's a bit nasty, so pay attention to this. Okay, and I already mentioned that we can have the options of taking the maximum average or the maximum of the minimum, and I already said that these options are not fully appropriate in the presence of uncertainty because sometimes they might lead to not wise decisions. Okay, so now let's go back to this table and then let's apply the utility theory. And as I anticipated to you, given now the full range of the possible benefits, I need to define the utility function for each of these benefit values by assigning, of course, utility 1 to the highest benefit, 79.22, and the lowest utility 0 to the lowest benefit, which is 61.18. Okay. This utility function, as I said, should be defined with interviews to the stakeholders. Let's suppose that it has this shape. This was done just by chance. And you see here in tabular form the utility function, and in graphical form there, from 0 to 1 is the utility, from minimum to maximum benefit is the benefit, and it has that form. And you see that probably it shows that the user, the stakeholder, he has or she has a quite significant propension to risk because it's below the 1-1 line, and therefore not the 1-1. Let's say that it's below the linear connection between 0 and 1 utility. Okay, good. In any case, now we have the utility function defined, and there are also techniques available. The literature suggests techniques to smooth the utility function because this kind of shape is not really meaningful from you know, a rational point of view. This clarifies this type of shape for the utility function, points out that the user, the stakeholder, doesn't have a clear idea of what this method means. And therefore there are methods suggested for smoothing it, for making the relationship more regular, and through the use of interpolating curves. But in this case, let's just stick on this, just in order not to make things more complicated. And then, let's try to move forward. So let's assume that we take the decision x1 equal 28, which is the optimal decision corresponding to W1, and in terms of benefit, therefore, we could get a benefit which corresponds to 79.22 with probability 1/3, and this corresponds to a utility of 1. So let me go back 1 second to the table. This is my table. So I'm now looking at this decision, 28. So the possible benefit are these three, 79, 74, 61. And I want now to compute the utility to associate to each of these possible benefits their utilities. This is what I'm doing here. So now I move forward. What I'm doing here is let me take into consideration the decision 28, and then I have a utility 1 associated to the first possible outcome. and the first possible outcome is related to a probability of 1/3. Fine. Then, another possibility is the second outcome, which has a utility of 0.6, and the probability again is 1/3. And so forth for the third outcome. Now, we will have 1/3 probability to get utility 1, 1/3 to get 0.6, and finally 1/3 to get 0, because the third option, the third possible outcome, is the minimum benefit. Therefore, we can compute an expected value of utility. 1/3 times 1 plus 1/3 times 0.6 plus 1/3 times 0, which means a result of 0.53. So, what is the meaning of this computation that I performed here? The meaning is that the user does not find any difference between x prime and a virtual decision that gives NB max with probability 0.53. This is the meaning. Of course, he doesn't know this computation, but he assigned, the stakeholder, he or she assigned a utility to each possible benefit. And therefore, the result is that to this decision of 28 corresponds a utility of 0.53, which means that in practice, he doesn't find any difference between assigning 28 and another hypothetical decision that gives to him the opportunity to get the maximum benefit with the probability 0.53. Of course, the same computation can be done for any possible